As physicists, we've eagerly anticipated this moment for over a century. Ever since 1916, this event marks a groundbreaking achievement, offering a glimpse into one of the universe's most intriguing and enigmatic phenomena: black holes. These cosmic giants, known for their immense power, remain incredibly elusive. While they are colossal in terms of their gravitational influence, they are nearly invisible to us, making them even more mysterious. One such black hole, potentially weighing between 2 to 4 million times the mass of our Sun, might be the subject of this discovery. Over the past few decades, the research devoted to black holes has transformed our understanding, taking us from a position of absolute ignorance to one where we are starting to get an intimate look at them. And now, things have taken an even more thrilling turn as physicist Michio Kaku has revealed that we have finally managed to peer inside a black hole. This revelation opens the door to a wealth of new information that could illuminate aspects of science that we may have previously overlooked. Let us take a deep dive into the realm of black holes and uncover what lies within them. While space is boundless and vast, the concept of black holes raises countless questions. Before we dive into the specifics of Kaku's remarkable findings, it's essential to understand the fundamental nature of black holes. Most people have at least a basic understanding of what black holes are, but significant gaps in our knowledge still remain. The theory of black holes dates back to 1916 when Albert Einstein published his general theory of relativity. This theory predicted the existence of black holes, though at that point, the idea was purely theoretical. It wasn't until about 50 years later, during the 1960s, that concrete evidence for their existence began to surface. Researchers studying the constellation known as Cygnus observed an anomalously bright blue star emitting X-rays. This star, they discovered, was not stationary but instead was orbiting a massive black object. Upon further analysis, it became clear that these X-rays were being drawn into this object, leading to the coining of the term black hole. This discovery was a monumental turning point because it confirmed that black holes were not just a product of Einstein's imagination. They were real, tangible entities that existed in space. It became evident that we needed to study them more thoroughly. Scientists from around the world began to focus their research on a particular black hole in the Cygnus constellation, designated Cygnus X1, which lies approximately 6,000 light-years away from Earth. This black hole was about 14 times brighter than the Sun and exhibited extreme density, with a gravitational pull so intense that not even light could escape it. This was the defining characteristic of a black hole: the ability to trap light within its gravitational grasp. The concept of a black hole is simultaneously fascinating and terrifying. A black hole is a region in space where gravity is so powerful that nothing, not even light, can escape from it. Any object that ventures too close to a black hole is sucked in, and once it crosses a critical threshold, it is lost forever, never to be seen again. This inherent danger is why it's so critical to expand our understanding of black holes. After the discovery of Cygnus X1, researchers began an exhaustive search for other black holes, and estimates now suggest that there may be over 100 million black holes scattered throughout the Milky Way galaxy. However, due to their nature, these cosmic giants are exceedingly difficult to detect, meaning that we don't have a precise count. What is clear, though, is that there could be millions of black holes within our galaxy, underscoring their importance in cosmic research. The main concern surrounding black holes revolves around their gravity. Their gravitational force is so immense that anything that gets too close is gradually compressed to an extreme degree until it becomes a singularity. To put it simply, black holes function as cosmic vacuum cleaners, pulling everything in with an insatiable force. One of the most alarming aspects of black hole research is that if someone were to fall into one, they would be stretched out into an elongated form due to the tidal forces acting on them. This stretching would happen gradually, and the person would perish before reaching the final phase of this process. So let's be clear, it's best to avoid falling into one at all costs. Even though the nearest black hole is located some 500 light-years away, this still raises questions about the potential dangers they pose to us. In 2021, a remarkable milestone was achieved when scientists successfully captured the first clear image of a black hole. This particular black hole was located in the galaxy M87. The research team took multiple images over several nights, and by stitching these images together, they created a comprehensive photograph that revealed startling details. It turns out that a black hole is not simply one giant void of nothingness, as many people might think. In fact, a black hole consists of three distinct layers. The first layer is called the event horizon. Once an object crosses this boundary, there is no turning back. It will inevitably be drawn into the black hole. The second layer is known as the photon sphere, a region where light itself can be trapped in orbit around the black hole. Any light entering this area will become ensnared by the black hole's gravitational force, unable to escape. The final layer is the singularity, where everything that falls into the black hole is crushed down to an infinitesimally small point. This is where the laws of physics as we know them break down entirely, and it's impossible to predict what might occur. What's even more fascinating and troubling is that no two black holes are exactly the same. While they all adhere to this three-layer structure, the way they operate can differ dramatically from one to another. Normally, scientists would rely on telescopes to observe celestial objects, but when it comes to black holes, this method is not practical because black holes are invisible. Scientists can only study them indirectly by observing the radiation they emit, along with the surrounding gas and dust. Sending probes like Voyager to explore a black hole is out of the question, as anything that crosses the event horizon would be drawn into the singularity, where it would be obliterated. Therefore, scientists must study these extraordinary objects through a two-dimensional lens, despite their inherently three-dimensional nature. One theory regarding the formation of black holes is that they are the result of collapsing stars. When a star burns through all of its fuel, it can no longer generate the energy needed to counteract gravity, leading to a collapse inward, which can ultimately create a singularity. In order to further investigate the nature of black holes, NASA scientists turned their focus to the core of the M87 galaxy. Here, astronomers observed a massive whirlpool of superheated hydrogen gas spinning at an incredible speed of 1.2 million miles per hour. The sheer force of this spinning gas should have caused it to fly apart, yet it remained intact. Scientists hypothesized that a colossal mass at the center of the galaxy, weighing as much as 2 to 3 billion times the mass of the Sun, was holding it together. This mass could only be explained by the presence of a black hole. However, black holes may not just be created by collapsing stars. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe the dynamics of a rotating black hole. Kerr's solution showed that rather than collapsing into a point, a rotating black hole would form a thin disk, a phenomenon known as the ergosphere. The ergosphere is a region surrounding the black hole where the laws of physics begin to break down. Kerr's solution also predicted the existence of an Einstein-Rosen bridge, commonly known as a wormhole. This hypothetical tunnel would connect two separate regions of spacetime, and in some theories, it could even link two parallel universes. If one were to fall into a black hole instead of being crushed, they might pass through this wormhole and emerge in a different universe or even at a different point in time. To understand how a wormhole works, we must first grasp the concept of spacetime. According to Einstein's theory of relativity, space and time are intertwined, forming a four-dimensional fabric. Objects with mass warp this fabric, creating a gravitational field that causes other objects to move toward them. Picture spacetime as a sheet of paper. If you place 2 points on it and draw a line between them, that line represents the path objects take through spacetime. If you were able to fold the paper, you'd create a shortcut between the 2 points, much like a wormhole connecting two distant regions of spacetime. Wormholes are not merely science fiction. They are a direct prediction of general relativity. However, no one has yet observed one, and they are inherently unstable, likely collapsing almost immediately. The potential for wormholes to serve as travel pathways through time and space has captivated physicists for decades. While the concept of traversing vast distances in an instant or journeying through time is undeniably exciting, the challenges are formidable. Einstein's special theory of relativity predicts that nothing can travel faster than the speed of light, which places an absolute limit on the feasibility of wormhole travel, at least with our current understanding of physics. In recent years, a particular type of wormhole known as the CER wormhole, after Roy Kerr, has captured the imagination of many. This hypothetical wormhole would connect two distant points in spacetime, potentially even linking different universes or different moments in time. Critics, however, argue that the Kerr wormhole may be unstable or impossible to traverse due to extreme radiation and the forces at the quantum level. Some physicists point out that Einstein's equations, used to describe black holes and wormholes, do not account for the quantum forces that govern subatomic particles. To truly understand these phenomena, a new theory that unites quantum mechanics with general relativity is needed. Such a theory, known as a theory of everything, could explain how the universe works at every scale, from the smallest particles to the largest cosmic structures. Michio Kaku, a leading theoretical physicist, has been working on this unified theory for decades. One promising candidate is superstring theory, which suggests that all fundamental particles are actually tiny vibrating strings. In this framework, the universe is seen as a symphony, with different particles corresponding to different vibrations of these strings. Superstring theory also provides potential explanations for black holes, wormholes, and other exotic phenomena by demonstrating how strings warp the fabric of space-time. Despite its promise, superstring theory remains highly speculative, as it requires extra dimensions of space-time that we cannot yet directly observe. These extra dimensions could be so tiny that they are effectively invisible to us. Some theorists suggest that these dimensions were more eminent at the beginning of the universe during the Big Bang, and that they collapsed as the universe expanded and cooled. Superstring theory's potential to explain black holes, wormholes, and the very fabric of the universe remains one of the most exciting frontiers of modern physics. As we continue to unravel the mysteries of spacetime, black holes, and the cosmos itself, there's no doubt that there is much more to learn, and perhaps even more to discover about the very nature of reality. As we stand on the precipice of such groundbreaking discoveries, one key realization remains. We are merely scratching the surface in terms of understanding black holes and their true nature. Michio Kaku's work in the field of string theory and the ideas surrounding quantum gravity have only begun to offer possible answers. Even though we've managed to gain a clearer image of black holes through technological advances, such as the Event Horizon Telescope and new methods of indirect observation, much remains beyond our grasp. The frontier of theoretical physics, specifically in the context of black holes and spacetime, is still an incredibly active area of research where much speculation and exploration await. In addition to their obvious role in influencing the fabric of spacetime, black holes have become central to discussions about the origin of the universe itself. As string theory suggests, the collisions of universes could lead to the formation of new ones, and black holes could be integral in this process. Such a theory could suggest that our universe might have been born from a collision of two previously existing universes, or perhaps it could even imply that we reside within a black hole itself, a concept that would certainly flip our understanding of the cosmos on its head. If this notion holds true, it could challenge everything we think we know about the Big Bang, and we might begin to view black holes not just as destructive forces, but as potentially creative ones that serve as a gateway to other realms or parallel universes. While the idea that black holes could act as portals to other universes or even be the key to understanding time travel is tantalizing, this concept remains within the realm of theoretical speculation. The mechanics behind wormholes and the ability to navigate through them remain a profound mystery. Even if wormholes are stable enough to form, there's a question of whether the extreme radiation and forces near these structures would make them traversable. Some physicists speculate that if we could stabilize a wormhole, it might theoretically allow travel through time or between distant points in the universe, but that remains a far-off dream, at least with our current technology and understanding. Moreover, if we look at black holes through the lens of quantum mechanics, we find ourselves faced with even more intriguing questions. The behavior of particles at the quantum level is fundamentally different from what we experience at macroscopic scales, and the laws of physics appear to break down entirely when we consider objects like black holes. This discrepancy between quantum mechanics and general relativity has been one of the most significant challenges in theoretical physics. Theories such as superstring theory offer a potential framework for reconciling these differences by introducing additional dimensions and offering new insights into the nature of gravity. However, this theory has yet to be experimentally verified, and much of its predictions remain untested. Theoretical physicists like Kaku are working tirelessly to unite these two great pillars of physics, quantum mechanics and general relativity, into a unified theory that can explain the full spectrum of phenomena across all scales. Such a theory of everything would not only provide a deeper understanding of black holes and other exotic objects in the universe, but could also illuminate the very nature of space-time itself. The concept of multiple dimensions, as predicted by string theory, may help explain the unseen forces that govern the universe. It suggests that what we perceive as a four-dimensional reality may actually be just a small slice of a much larger, more complex structure. Another area of intense study is the role that black holes play in the evolution of galaxies and the larger structure of the universe. The discovery that supermassive black holes exist at the centers of most galaxies, including our own Milky Way, raises further questions about their influence on the formation and behavior of galaxies. It is theorized that these black holes may be involved in regulating the growth of galaxies, controlling the rate of star formation, and even playing a role in the eventual fate of the universe. The idea that black holes could have such an influential role in shaping the universe adds another layer of complexity to their already mysterious nature. Moreover, the intense radiation emitted by black holes, the so-called Hawking radiation, named after the famed physicist Stephen Hawking, has led to fascinating discussions about the ultimate fate of the information that falls into a black hole. For years, scientists have debated whether information is lost forever when it crosses the event horizon of a black hole, a concept known as the information paradox. Hawking's groundbreaking work suggested that black holes might emit radiation that slowly causes them to evaporate over time, potentially resolving the paradox. However, this remains an area of active research, with no definitive answers yet. What's clear is that the study of black holes has not only provided us with remarkable insights into the nature of gravity, space-time, and the universe as a whole, but has also opened the door to a new frontier in physics. Black holes challenge our understanding of the laws of nature and continue to provide fertile ground for new theories and discoveries. As our observational tools improve and as we delve deeper into the quantum and relativistic realms, it is likely that we will uncover even more surprises, reshaping our view of the cosmos in the process.